Morning, everyone. Please excuse my cold. I'll try to enunciate as much as I can, as good as I can. My name is Joseph Villanueva. I'm the project management for this project.
Marianne Della,
Ryan Torres.
Dan Bernstein.
Erika Serrano.
Cody Namani.
Abukar Abdirahim.
And we're the engineers of ACE. So for this presentation, we will be talking about our robot, introducing the competition that it will be participating in. We'll also be talking about the hardware and software design of our robot. We'll talk about the milestones that we set and have accomplished, and then we'll finally talk about the budget. So what exactly is ACE? ACE stands for Autonomous Candle Extinguisher. So our robot is going to go avoid an IR decoy or a device that our professor has made and find a real candle and extinguish it in the first floor of the engineering building. As you can see in the video, our robot does just that. And just to talk a little more about the competition, just to add on to what the previous robot group has talked about, there will be 3 devices, 2 decoys and 1 candle spread out throughout the room, and we have to go and find the candle. And to do that, we had to create a robot that is autonomous, can find the candle, can navigate, know its location, and avoid walls and objects that it may run into. And this is a hardware block diagram of our system. On the right, you see all our sensors, how we're going to detect the fire, how we're going to put it out with the water pump. On the left is how we're going to control and navigate throughout the course. Different motors. We have a 14.8 volt rail, a 5 volt power rail, and a 3.3 volt rail. And I'll hand it off to Dan to talk about the motors and motor driver.
Thank you. So in order to make ACE mobile, we chose a 100-to-1 gear ratio with a 64 CPR, which is cycles per revolution encoder. The reason we chose this, our big factor was we didn't want torque to be an issue. Our robot weighs around 7 pounds, which is pretty heavy compared to other robots there. Some of them weigh like little wimpy robots. And to control these motors, we actually use a dual motor driver. The way the H-bridge works on the motor driver is that 2 switches, as stated S1 and S4, will be pulled up high and tell it to go clockwise. While to be counterclockwise, S3 and S2 will be pulled high to be counterclockwise. For our battery, we chose a LiPo battery that had a nominal voltage of 14.8. The reason we chose this is we want that little extra oomph to the robot, and we wanted it to hold more power. For our sensors, we chose an IR proximity flame sensor. As the video shows how our sensor is working. We chose this sensor for the reason that it has a really good range. The range for it is 4 to 5 feet. We can sense the candle far distance. Our placements are around 180 degrees. And how it works is if the candle is close by, you will see the voltage go low. And if it goes far, you'll see it at 3.3, where we started. For our other sensors, I'll pass it to Erica.
Thanks, Dan. So we use 2 types of proximity sensors in order for a robot to move smoothly throughout the playing field without crashing into anything, of course. So first off are the ultrasonic sensors. We chose the sensors because they are of great use when sensitivity is needed in order to detect any objects. It uses high frequency sound to detect and localize an object in a variety of environments. In the next slide, you can see the relationship between voltage and distance. As you can see, the relationship is linear. And on your right side, you can see how we arranged the sensors on our robot. As you can see, we placed them in the front so we could cover the whole 180-degree angle of our robot in order to protect it. Next off are the IR proximity sensors. We use the Sharp sensors. We chose the sensors because they were low cost, they have great range, they are small and perfect for small robots like ours. In the next slide, you can see the relationship as well. As you can see, the relationship is nonlinear. And notice that when the distance, when the distance reaches its minimum capability, the voltage drops dramatically. On the video, you can see how the sensors work. And on your right, you can see how we arrange the sensors. We place the sharp sensors on the sides of our robot in order to detect the walls. And the ones in the front, facing the front, we use them to back up the ultrasonic sensor. Next up is Cody that will tell you a little bit about our water pump.
Thank you, Erica. As you can see, we have a 6 to 12 volt rated pump, and we chose 12 volts because we didn't want it to exceed our 14.8 volt battery. It's also extremely lightweight, coming in at only 0.15 kilograms, and we chose it because we wanted it lightweight because we didn't want it to weigh down our robot. It also easily outputs 100 milliliters in an efficient amount of time. And as far as the nozzle goes, it's flexible and extremely accessible. That way, we could make adjustments and get in and out of it if we needed to. Last but not least, we have we had to customize our nozzle head for greater spray distance. We did this by drilling a small hole, and thanks to Mark Bruno's hand drill, I was able to go in there, drill a small hole, and that was able to accomplish a greater spray distance. I'll pass it on to Ryan and he'll explain SolidWorks.
So let's explore a little bit about our design layout. Here you can see the progression of our robot design. We started off 2 layers, then we went down to 1. We started and went to more of a 180-degree front end, and this allows our sensors to have a wide range to locate the fire. And we have a 3-layer design. So our bottom design, or our bottom layer is metal. It's where we attach the swivel wheel that we have on the front end, where we attach the motors, and we attach all of our sensors that are standoffs to about 3 to 5 inches, which is the desired candle height where we need to put out. And then we have the chassis, the middle layer, which is 3D printed. It's about 4.5 inches tall. This allows the space to put all of our components in, and it's a very open space with an attachable top of acrylic clear plastic that we mounted on with magnets so that we can get into our components with our modular design with headers, and we can replace them easily if something blows. And we utilize the water pump backpack design so that water doesn't get into our chassis at all. And here's the image of our actual robot. As you can tell, we designed our robot to perfectly and clearly, and this is the actual model that we have in SolidWorks. So as you can tell, the planning has been extensive, and we have our desired look.
Okay, so in order to have a successful communication between the hardware and software, we use a microcontroller PIC32 with 44 pin to control our robot. And we chose that part because it has enough analog to digital converter inputs, and it has 13 of them. We use 10, and it has also enough output for the pulse modulation output that we use for our motors and motor drivers. And next, we have a software flowchart that explains how we are navigating throughout the course. And we use this flowchart to implement our thoughts and design and think how to navigate throughout the course and detect while avoiding objects and obstacles and walls, and also detecting the infrared radiation, and also the flame and decoy test, and decide whether to distinguish between the flame and decoy. And to talk more about that, I will hand it to Joseph.
So the next couple of slides are going to be some important algorithms that we included in the program in order to accomplish the task efficiently. The first thing we have to do, and what we thought of, is how are we going to track where we are in the downstairs engineering floor? Are we going to be in room A, in the hallway? Depending on where we are, what sensors are we going to turn on and off? When should we turn, when should we not? So we do this by using dead reckoning based on distance traveled. We receive that information from the motor encoders. Each tick corresponds to certain angular distance that's traveled by the motor. And we also use the help of sensors. If we turn, we're probably in room A. If we turn again, we're probably somewhere turning in the corner of the next room. So all of that is what we had to think of when we're talking about creating an autonomous robot. And in the next slide, again, driving straight is really important. We don't want to run into walls. So what we did is created a proportional controller to get the number of encoder ticks, which means distance traveled from each motor, comparing them, gathering that difference, which is the error, and then multiplying it by a KP value, which is proportionality constant, which is 0.167 in our case, and then multiplying that and altering the speed of one of our motors to match the other. And next I'll hand it off to Abu to talk about how we figured out if the device we were looking at is a decoy or is a candle.
Thank you, Joseph. Now, as you might imagine, an important characteristic of our robot is being able to differentiate between a flame and a decoy. Now, a common approach to this is having two sets of sensors on the robot. One set would be the flame sensors that detect the presence of infrared light from either the flame or the decoy. You would then have another set of sensors that detect the presence of heat, since the decoy doesn't emit any heat. Now, we thought we were better than that. What you're looking at are actually waveform outputs from the flame sensors, depending on whether they're looking at the actual flame on the left and the decoy on the right. As you can see, both have very distinct signatures, and we created an algorithm where our microcontroller could be able to reliably tell whether or not what it was looking at was a flame or a decoy. Our algorithm is very accurate and very reliable. I'd like to pass it back to Joseph to talk a little bit about our project management and a few milestones we achieved throughout the process.
So here you can see a list of our milestones that we've set throughout the competition. This project was very much planned. A lot of these, we've completed all of these milestones. A lot we've completed ahead of time, some a little late, especially when we're trying to fully assemble our robot, have all the sensors functioning properly. We were running into an issue where the 3 ultrasonic sensors we set at around on 3 sides of our robot were interfering with each other. We had to compensate for that error, and we actually are using the side sensors instead now, the IR sensors, rather than having 3 operational ultrasonic sensors. And I'll pass it on to Marianne to talk about the budget.
Thank you, Joseph. So we have a budget of $750 to use throughout the semester, and as you know, motors and motor drivers sensors are the most essential parts in our design. So we use 30% for each, and 10% for the microcontroller and circuit components, 5% for batteries, and about 20% for replacement parts, shipping, and other replacement parts. And we used all of our budget, and now I hand it to Abu to finish up.
Thank you, Marianne. So we covered a lot in this presentation. We gave you an overview of the contest. We gave you an overview of our hardware and software for our robot. We talked about important milestones. We gave you an overview of our budget. We hope you enjoyed our robot. We certainly loved it. And the competition is later this afternoon in the engineering building, so we'd love for all of you to be there to watch ACE win this year's competition. Thank you.